Last week we had finished looking up the rest of the universal physical laws. So that is the four that were remaining, which is the principle of angular momentum, the principle of linear momentum, the first law of thermodynamics, and the second law of thermodynamics. And if you recall, that the purpose of this whole exercise with the physical laws was that we were deriving them here again because we were doing a special case of these universal laws, which is that we were looking at them for infinitesimal volumes or infinitesimal material elements. And now that was something which was new from what we're more used to. That is, when we had been considering these universal laws in our undergraduate studies or before that, we'd just been looking at them for entire bodies. Okay, so last time, is my voice clear or is there too much background noise? Thank you so much. Right, so last time I was trying to solve an example related to the thermodynamic laws, that is the first law and the second law of thermodynamics, and I had gotten stuck solving the second order differential equation. Now, first of all, Asif had solved it, and I think Asif had shared the solution with us. So you guys are welcome to just take a look at that, ताकि we can progress next. Secondly, as I had mentioned to you guys, that these two laws, we're just going to be dealing with them conceptually, and I don't want to get into the numerical aspect of the heat transfer related laws. So that's why I'm actually gonna go back and I've re-decided why was I even doing this when I'm saying that this is not the focus. So that's why I'm gonna skip this again. I'm going to skip this example, and I'm also going to reiterate to you guys that the focus for us in continuum mechanics course is just going to be conceptually understanding the first and second law of thermodynamics, whereas the sort of application of these laws for particular instances you will deal with in CFD1, CFD2, right? So that's why I want to move forward from there. So, right. So today we're gonna then move on to our next topic, which is looking at a very particular continuum medium, and that is the continuum material of the elastic solid. Now, again, as I said, there's a sort of, actually maybe I didn't talk about this, but let me just do it now. So media are generally broken down into two types. One is solids and the others are fluids. So solids tend to deform under loads, whereas fluids tend to flow under loads. Now the thing is, this is not a black and white distinction. Solids also tend to flow sometimes under certain conditions, whereas fluids also tend to deform under certain conditions. But of course, we're just dealing with some simpler materials to get us up and running and started with seeing how continuum mechanics can be is built up slowly and steadily, right? So that's what that with that caveat, I want to say then that that's why we're moving on to looking at first the simplest possible solid that we can look at, and then time permitting we are going to look at the simplest possible fluid that we can consider. Right now, as I said, because there are whole fluid mechanics courses dedicated to fluids, whereas as you might have noticed in your course selection, there are fewer ones for solids. That's why this course will not go into extreme lengths of detail for fluids, but whereas we will take perhaps 2 lectures for solids, which is again not that much detail, but still a little bit deeper, so that it is covered, since there isn't a course dealing with advanced mechanics of materials or linear elasticity and advanced stress analysis. So I believe, I've been told they aren't being offered right now. That's why I was just saying that caveat. Maybe somebody shows up and they might get offered next term. So you'll be more than welcome to take them. Okay, so with that, let's jump to this simple type of material. And first, let me explain why are we starting to look at a particular type of solid and what I mean by that in the context of continuum mechanics. Now, you guys may recall that we've been setting up the stage. We've been setting up the problem, which is that we've defined deformation measures. We've also defined measures of internal loading. Now we've also already considered universal laws which are applicable to all medium. And the purpose of that was so that we can start to reconcile our deformations with our loadings. ठीक है, मतलब ये है कि we are trying to reconcile कि how do we figure out कि एक particular material का क्या behavior होगा given a particular loading, how will it deform under a particular loading and whatnot. Now, as we've seen कि we need those universal laws because उन्हीं laws से हमें कुछ information मिल रही है which restricts how या फिर which sort of lays down some guidelines that how materials would be behaving, right? So for example, we saw that there is this principle of linear momentum, right? So from that principle of linear momentum, we had managed to derive our equation of motion. And in that equation of motion, we saw that, okay, if the body is having certain acceleration, then how do the stresses within that body relate to that acceleration, right? That's just one idea. Now, still, even with those universal laws, we are still not there yet. We're not at our goalpost. Because as you might imagine, those physical laws are applicable to every single material in the universe. But every single material in the universe does not behave the same way. So even though वही सारे laws सबके ऊपर applicable हैं, लेकिन of course उससे आगे भी कुछ material specific principles या laws are acting on particular types of materials, right? So why is it that if I apply a load to steel and I apply a load to water, the same load to water, why is it that steel behaves completely differently to water? उन दोनों के ऊपर वही universal laws लगने हैं. तो ऐसा क्या है? Now, वो जो specific चीज़ है which differentiates these materials is a material specific behavior. Now these material specific behavior are described using या फिर उनको कहने का तरीका ये होता है कि they are referred to as the constitutive behavior of the material. Constitutive meaning the thing that describes the material, that constitutes a material. Okay, so the reason why the steel behaves differently than water is because steel has a different constitutive behavior than water. Okay, so that's what we next need to do, which is to start to look at the constitutive, मतलब ये कि specific materials का क्या behavior होता है एक एक करके. Okay, now the nice thing about that is that not every single material behaves completely uniquely. मतलब ये कि we can actually define classes of materials, or that makes our life a little bit easier, but even then the classes are thousands upon thousands of different types of continuum. और इसी की वजह से जो continuum mechanics itself है, that leads to so many branches of mechanical engineering and so many different subjects within itself, because as I said, जैसे as you can see, the topic of today's particular behavior that we're going to be talking about is the elastic solid, right? So of course if we then look at some other solid, for example the plastic solid, so उसकी अपनी एक पूरी constitutive material behavior describe करना पड़ेगा, और वो that will take up an entire study of its own. फिर जी maybe viscoelastic solid, उसकी अपनी पूरी एक study है. फिर fluids के अंदर भी similarly there are loads of different classes of fluids, and so on and on. And it's exactly because of these thousands of different types of constitutive behaviors that we get this rich and diverse diversity within mechanical engineering. ठीक. So my point is everything that we've done so far, from our kinematics to our kinetics to then our physical laws, all of that was universally applicable, या फिर they were generally applicable to all continuums. Whereas now we are starting to look at specific material behaviors. Okay, so I hope that makes sense. कि इस तरह हमारे पास, that's how we've ended up with so many different sort of sets within subsets and subsets of how to analyze this behavior, how to analyze that behavior, and so on. Okay? It's because of these constitutive material behavior. Right. Now, next I want to go back, which is a little bit, this is going back to our first lecture basically, which is that we were discussing the engineering approach to continuum mechanics. Now, if you recall, हमने discussed ये हमने material parameters को तब भी mildly discuss किया था, and we were discussing के what is the engineering approach versus the physicist's approach. So we were discussing how us engineers, we tend to observe physical phenomena. That is, when I was saying that steel behaves differently and water behaves differently, so what we are going to do is we're going to test it. We're going to perform an experiment, and then we're going to figure out, okay, what is the constitutive behavior of steel, whereas what is the constitutive behavior of water. मतलब ये कि for engineering and the continuum mechanics that we are doing, these material behavior are derived experimentally. Okay? Whereas, as we said, physicists tend to do it in some other way, which is that they do calculations from first principles and they say okay, we can do it in that way rather than depending on observation. Right. Okay, so with that, let's jump into our first class of materials, and that is going to be our elastic solids. Or I was being a little sneaky, even within the elastic solids, we're actually going to be focusing on linear elastic solids, or slowly we'll start to see what each of these terms mean. What does linear mean? What does elastic mean? And solid we've already discussed, something that deforms under load rather than flowing. Okay. So I think आप सब लोग familiar हैं कि when we are trying to describe the behavior of a material, then we tend to define some new physical properties, right? So I think you guys have all heard of something known as the Young's modulus. I don't expect I need to go into that. So essentially, you know how we just said कि हम experiments perform करते हैं. So उन experiments से हम क्या चीज़ extract कर सकते हैं, वो फ़र्क चीज़ें हैं. So उन्हीं के अंदर depend करता है कि what type of test we're doing. So for example, if we are doing a uniaxial test, uniaxial मतलब it's just the load is being applied about one axis. Then if we plot our stress strain curve, the uniaxial stress strain curve, then what we end up seeing for our linear elastic material, and please note मैं linear elastic solid की ही बात करना शुरू हो गया अब directly, then we see a straight line. This is the thing that we observe experimentally. Now, as I was saying, when we see this straight line, we're going to try to characterize it, right? We're going to try to describe this behavior. So clearly, if I'm plotting the stress strain curve, a good idea would just be to figure out what is the gradient of this straight line, or is gradient को है हम Young's modulus कहते हैं, या फिर the elastic modulus even is the term given to it. So it's the gradient of the uniaxial stress strain curve. ठीक है जी. लेकिन इसी तरह हम और भी बहुत सारी physical observations कर सकते हैं. So we could, instead of performing a uniaxial test, we can actually be performing some other tests as well, including, for example, a torsion test. Or if we perform a torsion test, we are basically, the properties that we're finding are, instead of the stress and the strain like so, we are getting our shear strengths against the shear strain. So iska jo ratio hota hai, that then is known as the shear modulus represented by mu. Then finally, there's another type of test that we can be doing, and that's hydrostatic pressurizing. Matlab if we apply equal normal stress on a cube of a material, and see कि उसकी volume कैसे change कर रही है, then that type of a test we can find the bulk modulus of a material. ठीक? That is, we can define these different physical properties to suit our needs for what type of test we're doing or what type of property that we're considering. So I've mentioned these three. I skipped through the Poisson's ratio. Let me go back to it just for the sake of completion. So Poisson's ratio is basically when we are applying a, let's say in a uniaxial test, this is my uniaxial material and I'm pulling it in this direction, then what we observe physically is that as it extends in this direction, it tends to contract laterally. That is उसकी shape में थोड़ी सी contraction आ जाती है in the lateral direction. And Poisson's ratio gives us this ratio of the lateral strain to the uniaxial strain. Okay, so yep, things that you're familiar with. Now I just want to point out one more thing in this, okay, all of these, when we're talking about the linear elastic solid, are constants of linearity या फिर constants of proportionality for different versions of Hooke's law. ठीक, Hooke's law, I think सबको याद है. Hooke's was in the 1600s was the first one who observed that we see when he performed the experiments with springs, but it applies to materials as well, that the force and the extension in a spring are proportional to each other. And then he later moved on to looking at materials and saw that the same thing was happening. Right? So in this case, we have that the stress and the strain are proportional to each other, whether the stress be uniaxial or whether the stress be a shear strain or whether it be the hydrostatic stress and so on. So मतलब ये कि ये चारों जो material properties से हम familiar हैं, they're all a variation of or या फिर a different representation of Hooke's law या फिर a linear law. Right. Now, there are actually many more elastic constants than just these four, but these are the basic ones that we tend to be familiar with. आज ही हम देखते हैं कि let's see if we can introduce you guys to some other new elastic constants. Okay, so that will come later though. So let's move on to clarifying some further things about when we're describing a material. There are a few other things that need to be clarified. So first of all, if these material parameters that we've just discussed, for example, the Young's modulus, or the shear modulus, if the material has one Young's modulus in one direction and a different Young's modulus in another direction, then the material is said to be anisotropic. मतलब ये anisotropic. An matlab not, iso means same and tropic means direction. That is, it has different different elastic constants, different material properties in different directions. Okay, whereas if we have a material which has the same elastic constants in all directions, then it is known as an isotropic material. Iso again meaning same direction. So matlab all directions it has the same elastic properties, material properties. Now of course, just to clarify some examples of materials which behave anisotropically or isotropically, कुछ materials which have very sort of particular directional dependence of the structure. So for example, if you consider some materials which have fibers aligned in one direction, then you can imagine that material is going to be anisotropic. So for example, it might be much stronger in the direction of the fibers, whereas across the fibers it may be very weak. So that's one example of materials having strong directional dependence. So loads of materials we can think of which behave that way. So for example, naturally occurring materials tend to have quite a bit of structural directional dependence. So for example, wood is anisotropic. Composites that we ourselves manufacture sometimes tend to be very anisotropic, and so on. Whereas isotropic materials के अंदर generally metals we consider to be isotropic, uh, even ceramics, yep. But then it depends on the particular material. Ab already you can start to see कि ये मैं I'm still talking about the linear elastic solid. लेकिन even within the linear elastic solid, you can imagine that the anisotropic material has its own set of behavior, whereas the isotropic one is going to be much easier to define. So even here you can start to see कि कैसे अभी तक सब कुछ same चल रहा था और अब से onwards there is going to be so much complexity thrown into mechanical engineering. Next, to add to the complexity, if instead of talking about directional dependence, we now talk about positional dependence of the material properties. Matlab ye कि if I look at this wood and I can already see कि कुछ फर्क थोड़े से इसमें patterns बन रहे हैं. So what if I take a sample from here and test it and find out what is Young's modulus is, whereas if I take a sample from here and test it, it turns out that it has a different material properties. Then in this case there is a positional dependence, और orientation नहीं थी, direction मैंने वही ली थी समझे, लेकिन जगह change कर दी थी in the material. Then if I get different properties, then that material is heterogeneous, different behavior basically. Whereas if it has the same properties no matter where I take the sample from, then it is a homogeneous material. ठीक है जी. Now इसकी भी these things are not hard and fast. It depends on the scale that we are looking at. Let me give you an example. If you're looking at an alloy, और एक alloy ऐसा जिसके अंदर कोई फ़र्क grains बने हुए हैं और उनके फ़र्क phases हैं, let's say. So clearly I hope you guys can see कि कुछ grains हैं जो पूरे के पूरे white हैं, whereas कुछ ये pieces हैं जिसमें ये black और white की लाइनें बनी हुई हैं. So clearly if I take a specimen from here, that's going to have different properties than if I take a specimen from here. So this is going to be heterogeneous. लेकिन what if I take a sample जो इतना बड़ा हो and then test it? Then I think you guys can identify that this sample is already large enough that overall if I keep taking samples of this size, I will probably end up getting on average the same properties. So that is these descriptions of anisotropic and isotropic and homogeneous and heterogeneous and so on, they actually need to be carefully considered for our particular case, depending how large the sample we're taking and whether उसके अंदर कोई average response आ रहा है या नहीं. Right. So just keep that in mind. It's not a black and white कि yes ये material हमेशा ही isotropic होगा या फिर yes ये material हमेशा ही anisotropic होगा and so on. Okay. So let's now describe some of the things that we've already discussed for the linear elastic isotropic material. So we saw कि generally speaking वो हमने जो फ़र्क टेस्ट किए थे for the, let's say, the uniaxial case, we were getting a linear response. So that is why this material was being referred to as a linear material. That is, whatever loading that we are measuring with respect to the deformation in it, we see a linear response of the material. However, it is good to clarify that this, as you can see, I'm using my small strain tensor. मैंने green strain tensor नहीं use किया था. Why? Because this linearity often only holds true for small strains. Whereas if I start to go for very large strains, then there are hardly any materials which will still obey linearity. So that's why when we're describing linear elastic solids, most often, like 99% of the time, we're talking about materials for which we have small deformations. Okay, so two things right now. Oh, sorry, I jumped from 1 to 4, sorry for that. That we have a linear relationship between loading and deformation, and the deformations are small. Then the next thing is, let's move to the elastic part. Elastic basically means that the material returns to its original configuration when the loading is removed. That is, when I load it up, sure, it gets a strain in it, but when I remove the load, it comes back to its zero strain position. Okay, so the deformation disappears when the load is removed. And then finally, also another aspect of linear elastic materials is that it does not matter what loading rate, either epsilon dot or the rate of deformation tensor, remember D, which is the symmetric part of del V. It does not matter what rate we are applying the loading at, we get the same stress strain curve, or we get the same response basically. Okay, so these are some of the characteristics of linear elastic solids. Now, most commonly when we're doing our uniaxial tests, then we just have the stress and the strain plotted for one direction. But of course, we guys are interested in looking at the complete picture, like looking at the general three-dimensional stress state and deformation state of a material. So we want to actually be able to define the other stresses and the other strains as well. Now it turns out that when you have a linear elastic material, basically what we are saying for that is that the entirety of the stress tensor, that is all of the stress tensor, is actually linearly related, directly proportional to our strain tensor. Now how that's related is by I'm just going to show it to you guys, by something called the stiffness tensor, and again in a linear manner. In a linear manner. That is, for the linear elastic solid, its general 3D behavior is represented by this linear relationship right here. ठीक है जी? This is the 3D version of our familiar Hooke's law, जो हम sigma xx is equals to epsilon xx जो कर रहे होते हैं. That is 1D के अंदर जो हमने Hooke's law describe किया हुआ था. ठीक. Now please notice that when I'm talking about the 3D general behavior, then I am talking about the full stress tensor and the full strain tensor. And now they are being related by this fourth order tensor, which is known as the stiffness tensor, most commonly represented by C. Take. And then further, and we're not going through the proof of this, how this came about, just take my word for it again, this is just an experimentally observed phenomena. मतलब ये कि हम लोगों ने engineers and physicists and so on, we all mechanicians, we perform loads and loads of experiments for some particular type of materials, and we then classified कि अगर वो material ये linear elastic solid है ना, तो उसके लिए हमें हमेशा stresses, strains से इस तरीके से relate हुए हुए मिलते हैं. That is, this is the constitutive material behavior of a linear elastic solid. ठीक. Now let's just describe this in a little bit more detail to point out that this C times epsilon is actually a double dot product या फिर double inner product, such that if I write it out in index notation then this is what I'm getting. I have कि अगर मुझे sigma ij चाहिए, then I'm performing a dummy with two of the indices. K और L दोनों dummies हैं, and as you can see कि फिर that is it's a double inner product, then I get my sigma ij. Up you're welcome to check it. K, L दोनों would disappear, they're the dummies, and ij are just left. So this is consistent index notation wise. Now अब ज़रा इनको describe करने पे आते हैं. We all remember sigma ij is a second order tensor. Second order tensor का मतलब ये देखें ना, दो indices हैं. That means कि it has two directional dependencies as we had discussed in great lengths, and that it has then 9 components. अब इस 9 components को तो हम लोग इस 9 components को तो हम लोग easily matrix notation में represent कर लेते होते हैं ना. Similarly, epsilon KL is also a second order tensor. It is a dyad. So उनको भी हम matrix order में matrix की version में represent कर लेते होते हैं. But now what do we do about this fourth order tensor Cijkl? Now this is now going back to our second lecture and discussion in that, जिसमें हमने बहुत ही briefly इस equation को पहले भी देखा हुआ है और हमने इस पर touch upon किया था कि fourth order tensor का मतलब है कि इसके अंदर 3 to the power of 4 terms हैं. That is, there are 81 components inside it. And even हम third order tensor को भी sort of 3D array की तरह represent कर लेते हैं. But this fourth order tensor, okay, if we want to represent it and write it down on a piece of paper, on 2D piece of paper, then we need to come up with some other scheme and we need to manipulate this basically. And that's what we're gonna do. Basically is कि unfortunately, जैसे मैं अभी आपको कह रही हूँ, ये fourth order tensor को हम नहीं represent कर सकते directly as a two-dimensional matrix. So we're gonna have to change things up a bit. Now what we tend to do in order to be able to represent them is कि हम sigma और epsilon और stiffness tensor सबको थोड़ा सा फ़र्क फॉर्मेट में लिखना शुरू करते हैं. फ़र्क फॉर्मेट बीइंग कि वो जो 9 कंपोनेंट्स थे ना सिग्मा के स्ट्रेस टेंसर के, उन सब को ज़रा कंबाइन करके एक कॉलम के फॉर्म में लिख दें, समथिंग लाइक सो. प्लीज़ नोट, ये वही सिग्मा, नथिंग, जस्ट आई हैव चेंज्ड अप द वे वी आर राइटिंग अप दैट सेकेंड ऑर्डर टेंसर. ये उसके 9 कंपोनेंट्स यूँ होते थे ना, अब उनको उठा के इन्हीं सब को अगर हम एक कॉलम के फॉर्म में लिखते हैं. Now already I am being careful and I am representing these components of the stress tensor and the components of a strain and tensor with these double waves to show कि अब ये tensors की तरह नहीं लिखे हुए. मतलब ये कि अगर मेरे पास ये डबल वेव्स वाला है ना, तो वो जो मैंने टेंसर मल्टीप्लिकेशन नहीं करी थी, सिग्मा प्राइम इज इक्वल्स टू क्यू ट्रांसपोज था, सिग्मा क्यू, या फिर द अदर वे अराउंड. यू रिमेंबर व्हाट आई एम टॉकिंग अबाउट. आई एम टॉकिंग अबाउट द स्ट्रेस ट्रांसफॉर्मेशन केस. देन if I have my sigma written up like so, then this does not apply. मैं ये डबल प्राइम, ये डबल वेव्स वालों के ऊपर इस किस्म की ट्रांसफॉर्मेशन नहीं कर सकती. That transformation was only applicable when I had written down the tensor as it, मतलब the real representation of the tensor. Okay, so I hope that is clear. Now, there is a reason why we're doing this, is because अब हम उस 81 components of CIJKL जो है ना, उनको हम मैट्रिक्स फॉर्म में लिख सकते हैं, ठीक है जी। दैट इज़ कि अब हमने ये देखना 1 2 3 4 5 6 7 8 9 इसके वो हो गए 9 by 1, दिस इज़ ऑल्सो नाउ अ 9 by 1 वेक्टर। देन आई कैन एक्चुअली राइट डाउन वही जो मेरी टेंसर मल्टीप्लिकेशन थी एज ए मैट्रिक्स मल्टीप्लिकेशन, ठीक। So what it becomes, I'll show you on the next page what the matrix representation of C is, but just again to highlight that this is not, these are, this sigma double waves underneath, they are not tensors, they contain the components of the tensors but they are not tensors, ये vector form में उसी चीज़ को लिखा हुआ है, ठीक। So please note that, okay। So then let's just see what it looks like, and this is what we have. So writing our stress tensor components like so in column format and our strain tensor like so in column format, फिर हम अपने वो 81 components of our stiffness tensor को as a matrix लिख सकते हैं, where the double underscore is representing it. This is not the tensor representation of it, it is just to write it down conveniently on a two-dimensional piece of paper. ठीक? Does that make sense to you all? Perfect. I'm guessing that makes sense, that's why. Now, now does this not look extremely complicated? I said I'm looking at the simplest possible solid, the linear elastic solid, जिसको आप सारी ज़िंदगी analyze करते रहे हैं just using the Young's modulus, so nice and easy. और अब एकदम से उठ के हम देख रहे हैं कि अगर 3D में हम linear elastic solid को देख रहे हों, so we have 81 components. So that does not seem so nice. But luckily for us, God is great and He has made our life much easier than this. Or what happens is that we can actually use some of the principles that we've already discussed to figure out that in 81 में से independent components कितने हैं. Okay, so as now we're gonna start to just jump into how can we find how many of these 81 components are actually independent. Right.
मैम क्वेश्चन था
जी प्लीज।
मैम हमने पिछली स्लाइड के अंदर जो नोटेशन इस्तेमाल की है उसके अंदर ऑर्डर मैटर करता है?
Okay, so
जैसे हमने सिग्मा 1 1 सिग्मा 2 2 सिग्मा 3 3 उसके बाद
yes,
सिग्मा 1 2 2 1 2 3 3 3 1 1 3 इसी ऑर्डर में लिखना है हमेशा?
बिल्कुल। So basically order matter करता है in the sense के अगर आप इसका ऑर्डर चेंज करें ना, मतलब सिग्मा 1 1 के बाद सिग्मा 1 2 आ जाए, then what we're gonna have to do is कि we have to change the strain tensor correspondingly, and then we also have to, या फिर इसको भी ऐसे ही रहने दे बेशक, लेकिन वो confusion और ज़्यादा create हो जाएगा, but then we just have to keep our stiffness tensor consistent. मतलब ये देखें ना, मैट्रिक्स मल्टीप्लिकेशन हम करना चाह रहे हैं ना ताकि काम थोड़ा इजी हो जाए टेंसर के बजाय. सो वी देन हैव टू मेक श्योर कि वो करेक्ट टर्म्स आर लाइंग इन हियर एंड दे गेट मल्टीप्लाइड बाय द करेक्ट strain terms to give us our particular stress term. ठीक? So the point is being कि the order just needs to be consistent. That's it. ठीक है जी. अगर किसी को ये लग रहा था कि I expect you guys to memorize this, of course not, right? Okay, so we were trying to simplify our stiffness tensor, and I was saying that we're going to use some of the physical laws that we've already considered to see how we can do that. So you may recall that already we had used our principle of angular momentum for an infinitesimal volume to establish that the stress tensor is symmetric. राइट मतलब ये कि स्ट्रेस टेंसर अगर सिमेट्रिक है तो आई नो कि सिग्मा 1 2 और सिग्मा 2 1 तो दोनों इक्वल हैं, तो मुझे क्या ज़रूरत है कि मैं ये पूरा सिग्मा 2 1 का रो को लिखूं. So I can just eliminate this one from our matrix multiplication. So one aspect is not just कि वो matrix multiplication simplify हो जाती है, but also if I just look at my expression, then I hope you can already see कि if I can swap around the order of I and j and I should get the same ji, तो यही चीज़ stiffness tensor के अंदर भी होनी चाहिए कि thenCijkl should actually be equal to Cjikl so that I get the same stress tensor. That is that I get the symmetry of the stress tensor. Okay, so that is already because of that, ये मेरी पिछली slide से है, because of the symmetry of the stress tensor, this implies one type of symmetry of the stiffness tensor, and already I can eliminate कि ये 9 से इधर on the left hand side 9 से these should just be 6 by 1 हो गई, और here अभी the rest will still remain क्योंकि it's the stress tensor which is symmetric right now that I've used. Now इसकी वजह से I may forget, so I apologize for that, but 81 से I believe we are gonna get down to 54 from this. How? 3 rows निकल गई ना, और 3 times 6. Nope, not quite. In any case, I may be forgetting, or this is not important, so that's why I have forgotten as well. But certain number of components have been reduced from our symmetry, from our stiffness tensor. Now, I just want to point out one thing कि ये जो चीज़ हमने इन्वोक की है, इसकी वजह से as I'm calling this कि the left two indices of the stiffness tensor can be swapped. That's why this is called left symmetric. ठीक है, only these two left components can be swapped together. Also note कि वो दोनों right next to each other थे, तो इस वाली symmetry को ना actually minor symmetry भी कहते हैं, क्योंकि वो जो दोनों जो सिग्मा वाले इंडिसेस हैं वो आपस में स्वैप हो रहे हैं. ऐसा नहीं हो रहा कि ये आई जे जो है वो स्ट्रेन वाले इंडिसेस से स्वैप हो जाएं. सो दैट्स व्हाई दिस इज माइनर सिमेट्री एंड लेफ्ट माइनर सिमेट्री. ठीक, perfect. So I think you guys can foresee what's coming up next. So if I've just invoked the symmetry of the stress tensor, I think the strain tensor is also symmetric. वो तो by definition symmetric था. So let's use that, right? So if I have my strain tensor being symmetric, that is epsilon 1 2 is actually equal to epsilon 2 1, and similarly epsilon 2 3 equal to epsilon 3 2, and 3 1 is equal to 1 3, and so on. Then if I actually perform the multiplication, what I can do is कि इन दोनों की टर्म्स को मैं साथ ही कंबाइन करके, सो इन दोनों के कौन से कॉलम्स होंगे जो मल्टीप्लाई हो रहे हैं? इट्स द 1 2 3 4th and the 5th column, 4th and the 5th column, which are being multiplied by the same term, right? So I can just add them up to write them as one column, और इससे मेरे कुछ कॉलम्स अब रिड्यूस हो गए हैं ऑफ माय स्टिफनेस टेंसर. नाउ आई वांट टू फर्दर डू सम मैनिपुलेशन एंड नोट कि अगर हम एक्सपेरिमेंटली यही चीज़ टेस्ट कर रहे होंगे तो आई एम नॉट एक्चुअली गोना बी एबल टू डिस्टिंग्विश कि ये ऐड हो के क्या टर्म बन रही, मतलब आई एम नॉट गोइंग टू बी एबल टू डिस्टिंग्विश के एक ये अलग टर्म है इसमें और इसमें एक और अलग टर्म ऐड हो रही है. इंस्टेड मुझे इन कॉलम्स का सिर्फ समड अप वर्जन ही एक्सपेरिमेंटली अवेलेबल होगा, या फिर आई एम ओनली गोइंग टू बी एबल टू फिगर दोज आउट डायरेक्टली. सो इसकी वजह से आई कैन जस्ट अज्यूम कि हाँ भाई ये दोनों जो है ना ये भी इक्वल ही है एक्चुअली, एंड कंबाइन देम अप एंड से के नाउ इट जस्ट गॉट 2 times one of them. That's one way to look at it, to use experimental arguments. But the second one is looking at index notation. Sorry for that, I was just too excited about the stiffness tensor. I love the stiffness tensor and its symmetries and how we can manipulate it. So I got carried away and forgot to look at the time, right? So where were we? We were talking about how we can reduce, or how we can figure out how many independent components there are in this fourth order stiffness tensor. और अभी हमने पहले स्ट्रेस की सिमेट्री से या फिर प्रिंसिपल ऑफ एंगुलर मोमेंटम की वजह से जो हमें इंफॉर्मेशन मिल रही थी उसकी वजह से हमने स्टिफनेस टेंसर को थोड़ा सा रिड्यूस किया था, और अब हम strain की symmetry impose कर रहे हैं. And as I noted for the case of the stress one, here even the symmetry of the strain tensor leads to basically these two K and L being symmetric or swapped together. SoCijkl is actually going to be equal toCijlk. ठीक, इसकी मैं आपको एक एक्सपेरिमेंटल आर्ग्यूमेंट ऑलरेडी प्रोवाइड कर चुकी थी, विच इज़ कि अगर हम एक्सपेरिमेंटली वी ट्राइंग टू फिगर आउट द स्टिफनेस मैट्रिक्स, देन हमें नहीं पता चलना कि इसके अंदर क्या टर्म्स ऐड हो रही हैं, हमें एक्सपेरिमेंटली सिर्फ ये पूरी की पूरी टर्म ही वी कैन फाइंड आउट. Okay, so that's why what we just do is we assume that we're going to consider it to be equal, and then hence just have 2 times that particular component. That's one reasoning. But the second one is just using index notation, or index notation ki if I know कि epsilon is symmetric, so these indices can be swapped together, and that must also be the case in my stiffness tensor. Okay, so either these arguments work. Now, yep. Secondly, as we were Ji.
Ma'am, there is a question. Ma'am, when we did the stresses part, it affected the rows of the stiffness matrix, but we did not add the rows up. We just neglected the 3 from when we shifted from 9 to 6 terms. But while considering the strain part, we added the columns.
Yes. Yes. So just think about it that this is actually an equality, right? So we're saying stresses are equal to the product of this and this. ऐसा है ना, तो मैट्रिक्स मल्टीप्लिकेशन हो रही है. सो अगर तो कोई चीज़ लेफ्ट हैंड साइड पे हमें सिमेट्री हो हमारे पास, मतलब ये लेट मी गो बैक वन मोर which is to point this out. If I already know कि मेरे पास sigma 1 2 is equal to sigma 2 1, so that tells me कि why should I go to that extra length, और मुझे इस रो को फाइंड करने की ज़रूरत ही क्या है, राइट? मैं तो जब मुझे sigma 1 2 पता चल गया तो मुझे sigma 2 1 पता चल गया. इसकी वजह से we had eliminated that row. Whereas when we have, so we're eliminating some of these rows, right? We're eliminating this one, probably 3 2 को eliminate कर देते हैं. Whereas for the case of the strain, case of the strain, if these two are equal to each other, we can't just take them out. Instead, what क्योंकि हो क्या रहा है, जैसे अब मैं किसी भी एक रो को देख लूँ, लेट्स मी टेक सिग्मा 1 1 को ले लेते हैं, ज़्यादा आसान है, ऊपर पड़ा हुआ है. सिग्मा 1 1 के अंदर ये दोनों टर्म्स आ रही हैं, क्योंकि इनका कौन सा वो मैं एक ना कॉलम देख रही थी, 4th and 5th. When I take this whole thing and multiply it by this column, then what's happening? Epsilon 1 2 and epsilon 2 1 are going to get multiplied by these two terms, this one and this one. So that's why to find sigma 1 1, I do need these two. I can't eliminate them, but all I can do is to note that if they are equal, फिर I only need to multiply it by one of them, और उसके जो दो respective stiffness tensor के components थे, उन दोनों को आपस में add कर लो. Does that make sense?
Right.
Okay. Has anyone been keeping a track of how long my cough has been going on for? I think this has become such a persistent, तो 2-3 months होने वाले. This has never happened before. Sorry for that. Okay, so Yep, so I was just honing on the arguments that why am I combining these two, जो ये summation की term है, why am I combining them together and instead just assuming that they are equal, that is I'm assuming that there is symmetry of the stiffness tensor in these two indices such that I can then write this equation of my matrix multiplication. Now as before, because it's just these two right, this time it's the right two terms that are being manipulating, this is referred to as the right symmetry. And again, because it's only the indices of one of the terms, this time the strains terms, this is again the minor symmetry of the stiffness tensor. Okay, मतलब ये कि वो अंदर ही जो एप्सिलॉन की थी इंडिसेस वो दोनों स्वैप हो रहे हैं. ऐसा नहीं हो रहा कि स्ट्रेन की इंडेक्स, स्ट्रेस का इंडेक्स स्ट्रेन वाले इंडेक्स से स्वैप हो गया. ओके, अच्छा जी, नाउ लेट्स कैरी ऑन इन आवर इससे भी अगेन आई एम सॉरी, मेरा वो 81 से 54 से पता नहीं जहाँ तक पहुँचना था वो थोड़ा सा हिला हुआ है, बट आई थिंक नाउ वी आर एंडिंग अप गेटिंग a 6x6 matrix. So whatever it may be, this time I'm going to be correct. 81 so we're going to get 36 terms now. Currently, this is a 6x6 matrix. So we've reduced quite a significant portion. But lucky for us, we can reduce it even more. और उसके लिए जी प्लीज
माइनर सिमेट्री को एक दफा रिपीट करते हैं.
माइनर सिमेट्री का सिर्फ और सिर्फ ये मतलब है कि ये जो इसके ये दो हैं ना, ये दोनों में सिमेट्रिक है. वो के एल को हम स्वैप करके एल के कर दें सिमेट्री, राइट, दैट्स वाई इट्स जस्ट माइनर. अभी मैं आपको मेजर सिमेट्री दिखाती हूँ, सो जस्ट गिव मी 1 सेकेंड. जब वो आएगी तो खुद ही समझ आ जाएगा कि ये क्यों माइनर है, वो क्यों मेजर है. ओके, so yes, so we're trying, I'm saying there is more to this. So what's more, let's see what's happening. So before that, let me manipulate something and basically remove this 2 from here. और ये जो 2 हमारे पास stiffness tensor में आ गया है, उसको यहाँ से हटा के ना strain में ले जाते हैं. That is, what if I just move these 2's in here? थर्ड फोर्थ फिफ्थ सॉरी फोर्थ फिफ्थ सिक्स्थ वाले कॉलम्स की टर्म्स हैं, तो these are the ones. So then I can remove these 2's from here. And now I want to note, you might have forgotten this, but we did previously also discuss very quickly something, that there are 2 types of shear strains. ये देखें, ये shear strains थे by the way, epsilon 1 2, epsilon 2 3, epsilon 3 1. That there are actually 2 types of shear strains. One is our टेंसोरियल shear strain. टेंसोरियल मतलब ये कि वो जो shear वो जो स्ट्रेन टेंसर के अंदर shear strain होता है वो वाला. लेकिन एक और चीज़ होती है जो कि होती है engineering shear strain, जिसको हम वेरी फ्रीक्वेंटली गामा से रिप्रेजेंट करते हैं. और गामा, द engineering shear strain is actually equal to twice the tensorial shear strain. So that's extremely useful कि ये एक चीज़ वैसे ही engineers ने पहले भी define की हुई थी, तो उसकी manipulation से हम इस expression को फिर वो 2's को gammas के अंदर incorporate कर लेते हैं, such that now our matrix multiplication of our 3D Hooke's law is looking better and better. ठीक है जी. 2 निकालना और भी अच्छा है क्योंकि stiffness tensor के अंदर 2 not so nice. How can I carry on representing it like a indices and so on, ठीक है. Whereas strain की तो कम terms है, उनमें 2 डालना is easier. Okay, so अभी I've just manipulated thus far. Now let me move to the major symmetry of the stiffness tensor. Now I am actually not going to go into the details of this, and what I've done is that your assignment number 4, which I will be uploading tonight or tomorrow morning, that's going to deal with you looking at, okay, why is there major symmetry of the stiffness tensor. और major symmetry क्या है, अब गौर से देखें कि indices के साथ क्या हो रहा है. This ij together, if we move it and कंसिडर कि सिमेट्री इस तरह है कि ये आई जे और के एल पूरे के पूरे को स्वैप कर दें, अगर मतलब ये कि this is equal to KLIJ, then this is just its major symmetry. It's major because वो IJ तो stress के components थे और वो जो KL हैं वो तो strain के components हैं. So this is a major symmetry if we can actually write this down as, let me figure this out, KLIJ epsilon KL still. If we are able to do this, this is referred to as its major symmetry. और इसका जो reason है ना वो actually जब कोई मटीरियल डिफॉर्म हो रहा है तो उसके अंदर जो वो स्टोर्ड डिफॉर्मेशन एनर्जी स्टोर की हो रही है उससे रिलेटेड है बेसिकली. So as I said, assignment number 4 will deal with that in a little, for like not too much in depth but a little bit. Okay, so it will deal with the major symmetry of the stiffness tensor, right? That then finally brings us okay, this last bit has significantly reduced now. अभी आखिरी में हम 36 तक पहुंचे हुए थे. Now with the major symmetry in place, this 81 gets reduced to 21 components of the stiffness tensor. Or what we get is कि जो मैंने last page पे लिखा हुआ था right here, it's just कि this thing, this matrix right here is symmetric. And these are the 21 independent components of the stiffness tensor. Now, extremely useful, of course. Some of the universal laws we've invoked to get it down. But still, this is quite a lot. I hope you guys can reflect on that, right? So what this is saying is if I have to describe a linear elastic material fully in 3D, मुझे उसका अगर 3-dimensional response चाहिए, then I need to find 21 material parameters. It's quite a bit, but it is what it is. Right. Just a few comments here. Going back to the comment of what happens if we change the sequence of these stresses and the strains. I know I said you just have to keep it consistent, but जो अभी हमने manipulation की थी ना वो IJ की minor symmetry and then the major symmetry, उसको easily manipulate करने के लिए इस particular order ये वाला sequence use किया गया था. If we don't use that sequence, then थोड़ा सा इसको ना end में आके perhaps मज़ीद rearrange करना पड़ा होगा. So that's why it's this order, this particular sequence that is used. That is the normal stresses first and then the shear stresses, or the normal strains first and then the engineering shear strains. However, the analysis can still be done, it'll just be more complicated. Okay, so yes, so nice and neat, our constitutive relationship for a linear elastic solid has become much simpler than the tensor version that we had started off with. Okay, so just want to highlight again this fact that now here we have these engineering shear strains, and in case someone does not remember, let me just show you pictorially what these two are. So this is the tensorial shear strain, और basically tensorial shear strain क्या है, वो अगर हम अपने एक material element को shear होता हुआ देखें, observe करें, then this change in angle, this decrease from 90 degrees, इसका जो average है ना, मतलब ये कि half of this total change, that is our tensorial shear strain. Whereas जो engineering shear strain होता है, that's the total decrease from 90 degrees. Yep, so that's just a little reminder of these two versions. Okay, right, so our stiffness matrix now, by the way, no longer a stiffness tensor. Now the way it's been written up right here, this is a stiffness matrix. What we can do is we can invert this matrix equation actually to get the other direction, that is to figure out the strain. Oh, okay, sorry, getting ahead of myself. There's one more part left in the previous version, sorry for that. Yes, which is okay, yes. Which is still when we are trying to write these down, these 21 independent components and so on, ये 4 index लिखना is a bit too long, and this is too time consuming basically. So what we tend to do is कि हम एक और convention introduce करवाते हैं, which is known as the Voigt-Kevin notation. And in that what we do is कि हम उन जो डबल इंडेक्स स्ट्रेसेस हैं या डबल इंडेक्स स्ट्रेन्स हैं उनको सिंगल इंडेक्स से, और जो 4 इंडिसेस हैं ऑफ द स्टिफनेस टेंसर या स्टिफनेस मैट्रिक्स उनको 2 इंडिसेस से रिप्रेजेंट कर देते हैं. मतलब ये आपको याद है, ये पहले 3 नॉर्मल स्ट्रेसेस थे और ये पहले 3 नॉर्मल स्ट्रेन्स थे, और ये जो नीचे वाले थे 3 वो शेयर थे. तो हम क्या करने लगे हैं कि हम वो डबल इंडिसेस को एक इंडेक्स से रिप्रेजेंट करने लगे हैं. सो सिग्मा 1 देन दिस रिप्रेजेंट सिग्मा 1 1, sigma 2 represents sigma 2 2, sigma 3 represents sigma 3 3, and then sigma 4 for the one shear strain, and so on. Similarly for our epsilons. So इससे हमने क्या किया है, हमने ये 1 to 6, अब प्लीज़ बी वेरी केयरफुल, ये 1 से लेके 6 जा रहा है इंडेक्स. This is not tensor notation. Again, बड़ा बड़ा, don't get confused by it. And we are, क्योंकि you remember tensor notation में each index goes from 1 to 3. इधर हमने बस नए numbers introduce करवा दिए हैं ताकि हमें वो लंबे बार बार ना लिखने पड़े. Okay, so this right here, this is 1 2 3 4 5 6 are just names. They're like Sana, Abdullah, this, that, and so on. Okay, so this is just a name. और correspondingly इसी तरह पर हमारे stiffness matrix के sort of subscript भी change हो जाता है. Okay, now this is just to write it more compactly, and it is known as the Voigt-Kevin notation. Or as I said, this is not tensor notation. None of these things right now are tensors, so they do not, उनके ऊपर कोई tensor operations फिर काम नहीं करते. So वो जो stress transformation हमने पहले देखी थी वो इसके ऊपर काम नहीं करेगी, because this is not a tensor now. It's just the components of a tensor, but it's not a tensor. Okay, so now let me it's hair symmetric abhi, as I discussed. Now let me go back to where I was, which is that we can actually invert that matrix relationship to actually write down the strains in terms of the stresses. And when we when we do that, then we can represent it, as I said, in the opposite way, which is we can find the strains in terms of the stresses. Note here that I have used the Kevin-Voigt notation, so इसलिए 1 से लेकर 6 तक. और अब the matrix जो strains को stresses से relate कर रही है, that is the inverse of the stiffness matrix, is known as the compliance matrix. और अजीब सा पैराडॉक्स है, लेकिन compliance matrix is represented by an S. मतलब ये कि compliance is with an S and stiffness is with a C. I should look up why that happened historically, but yes, this funny little convention exists. Okay. And because the stiffness matrix is symmetric, so the compliance matrix is also symmetric. Okay, perfect. So moving on. Right, now something even more interesting comes along. So abhi tak we've seen that we have these for a linear elastic material. A solid, we need how many? 21 independent components to characterize its constitutive behavior. Now, वही बात कि जिस तरह universal laws were applicable to everything, and then we had a special case that we're looking at, that is the linear elastic solid. So it turns out that even within the linear elastic solid, there are special cases within it, right? So what happens is that certain materials behave in an even more specific manner, जिसकी वजह से ये 21 से भी कम हो जाते हैं for that class of material. So that's what I'm going to start to discuss now, or we can go through it pretty quickly. And the main aspect of what causes this to happen is कि कुछ materials के अंदर, मतलब material itself के अंदर, there tend to be some symmetry. Okay, so मतलब ये कि the material behaves in the same way, perhaps in one direction. So उसकी वजह से हमारे ये जो components थे 21 से, they start to get reduced even more. Okay, I don't think I explained it that clearly, but उसके लिए ना, let me just show you an example. So consider right here that I have a crystalline material. It's just easiest to do, to explain the symmetry planes using crystalline materials. So I have this crystalline material and I'm looking at its unit lattice right here. और अभी मैंने एक बड़ा ही अच्छा symmetric किस्म का वाला crystal lattice बनाया है. Now notice कि if I was to consider कि मैं कोई maybe अपने एक्सिस की रोटेशन परफॉर्म करूं, जिस तरह हम पहले भी करते थे, जब हम याद है जब स्ट्रेस की ट्रांसफॉर्मेशन कर रहे थे. सो वी यूज्ड टू यूज़ दिस ट्रांसफॉर्मेशन मैट्रिक्स जो मैंने कहा था कि हमें गिवन होगी, हम फिगर आउट नहीं कर रहे, और उससे हम स्ट्रेस को ट्रांसफॉर्म कर रहे थे. तो उसी तरह ना, जिस तरह हम स्ट्रेस को ट्रांसफॉर्म कर रहे थे, उसी तरह हम अपने CIJKL वाले स्टिफनेस मैट्रिक्स, स्टिफनेस टेंसर को भी ट्रांसफॉर्म कर सकते हैं. मतलब ये कि let's say कि I know my CIJKL, my tensor, my stiffness tensor in the X, Y, Z components, but let's say I want to find it in some other coordinate system. That is, I'm trying to find this thing right here, CIJKL prime. अब कुछ materials के अंदर मैंने जैसे कहा कि कुछ ख़ास बात ये होती है कि in particular directions it may turn out that even the transformed stiffness tensor is actually the same as our original stiffness tensor. So for example, मैं आपको इसी ये जो मैंने इधर crystal structure बनाया हुआ है, इसको अगर आप गौर से देखें, I think we can all identify that if I perform a rotation, let's say 180 degrees about the y-axis, if I do that, मुझे actually वापस यही shape इधर आके मिल जाएगी, यूँ करके, बिल्कुल वही चीज़. That is, I have just pointed out to you guys कि this material, ये मैंने बहुत ही बुरी diagram थी, but this material actually has some symmetry in its crystal structure. And because of this symmetry, those 21 components of ours actually get reduced even further. Okay, so now let's start to see कि ये कौन से ख़ास particular materials हैं जिनमें ऐसा हो सकता है. So first of all, let me consider a crystal structure जिसमें कोई symmetry नहीं है. Okay, और मैंने इसीलिए ना, वो मैंने आपको कहा था मैंने बड़ा simple सा बनाया हुआ है. इधर इस वाले material को का unit lattice को देखें. इसके अंदर if you look very closely, बड़ी छोटी छोटी minute सी बातें हैं, लेकिन they're important, which is कि these angles in the unit lattice, the alpha, the beta and the gamma, as you can see कि ये वाली जो line है, ये y axis पे line ही कर रही, मतलब ये कि ये alpha is less than 90 degrees. उसी तरह अगर हम इसको इस साइड से व्यू कर रहे होते, we would have seen कि even this beta is actually less than 90 degrees and even this gamma is less than 90 degrees. Or to add on top of it, this A, B and C are just not equal to each other although actually that doesn't really matter so long as these three are less than 90. अब इस किस्म का जो मटीरियल है, just please, I was just going into detail. You guys don't need to remember कि जी ये यूनिट लैटिस के एंगल्स क्या होते हैं एंड सो ऑन, इसीलिए वो मैंने स्लाइड पे इंफॉर्मेशन नहीं लिखी. Just the point is that this material is completely anisotropic. इसके अंदर कोई सिमेट्री नहीं है. So there is no plane या no axis of symmetry that exists in this material, and this one is known as a triclinic material. Okay, it is completely anisotropic. Okay, so this one of course then has the same old 21 stiffness coefficients as we have discussed, क्योंकि it is still linear elastic. Okay, so ये सबसे general linear elastic material है अभी जिसकी हम बात कर रहे हैं. Now let's start to consider materials which have some symmetry. So the first one that I'm going to look at is known as the monoclinic material. और इस material में there is one plane of symmetry. Now if you look here, in this case the gamma is actually equal to 90 degrees. इसलिए this जो C line triclinic major थी, this one is actually lying on the Z axis, and that's why this plane of its, ये वाला जो face है ना, this is actually a plane of symmetry. If you perform a reflection about this plane, you will get back the same unit lattice. So just the details irrelevant for us in this course. Just the point being that once we've got one plane of symmetry in this material, then we have reduced our material parameters to 13. और वो क्या 13 है? Look here, some of the shear components, ये जो shear strains के थे, they have gone to 0. Okay, and only one shear strain का component रह गया है, which will be causing stresses. Okay, so 13 material parameters. Let's then carry on with this idea कि planes of symmetry ज़रा increase करते जाते हैं. अगला हमने plane of symmetry डाला तो two अगर planes of symmetry हो. Now it turns out if you have two planes of symmetry, then उन दोनों planes के perpendicular जो तीसरा भी होता है ना, that's also a plane of symmetry. So whenever something has two mutually perpendicular, two planes of symmetry, then there is actually a third plane as well. And as I've drawn out here, in this case, all of the alpha, beta, gamma, the lattice angles are all equal to 90 degrees. This material is known as an orthotropic material. Orthotropic direction, ortho, so three, मतलब ortho मतलब perpendicular. So in this case, perpendicular directions के अंदर it behaves in a similar way, so to speak. So that's why we end up getting these 9 material parameters. और compared to the previous case, हो क्या गया है सिर्फ, I'd like to point out from the monoclinic material is के अब ये तीन भी और ये वाला भी गायब हो गया. So these ones disappear and we just have these shear components right here. Okay, another fancy one is something which has 3 mutually perpendicular planes, but also उन 3 mutually perpendicular में से एक plane के अंदर अगर वो isotropic हो, मतलब ये कि doesn't matter आप किस direction में उसको देखें, let me explain. Doesn't matter कि आप उसे इस डायरेक्शन में देखें या इस डायरेक्शन में देखें या इस डायरेक्शन में देखें, या मैं इस वाले की बात कर रही हूँ by the way. It has the same material parameters. Then in that case वो 9 से मज़ीद simplify हो जाता है and we just get 5 material parameters. And an example I've shown right here of a fiber-based material. Kashif had already pointed out fiber reinforced composites, for example. So then they'd be behaving like so. They have 3 planes of symmetry and then one plane जिसमें isotropic behavior है, such as this one. मतलब ये कि इसको आप इस direction में देख लें, इस direction में देख लें, इस direction में देख लें, in all the directions you're just hitting perpendicular to the fibers, right? So in this case, we have 5 material parameters. So as you can see, depending on the material, we can actually simplify our stiffness matrix even more considerably, right? So agar wo general anisotropic hoga, then we're stuck with 21 things we need to know to define that material. Whereas if we have some more information about that material type, then we can narrow things down even further, eventually getting to complete and utter isotropy, that is, getting a completely isotropic material, in which case we have an infinite number of planes of symmetry. Then we just have 2 material parameters. और ये 2 material parameters, oh sorry, again remember this is symmetric, so I've forgotten to show the symmetry wala triangle, but just note कि वो 2 क्या हैं, just this C11 and this C12. Now I think you guys may be able to identify these 2 material parameters as something else as well, which is कि for the isotropic material, this is the one जो हम undergraduate में बहुत ज़्यादा देख रहे होते हैं. I think you guys recall that we always need to define its Young's modulus and its Poisson's ratio. That is, you guys recall that for an isotropic linear elastic materials, we just need 2 material parameters to define it. Or आमतौर पे we take those 2 material parameters to be the Young's modulus and Poisson's ratio. Now I've just shown you that जब हम कंटिन्यूम मैकेनिक्स की डेफिनेशन से हमने शुरू किया, स्टार्टिंग फ्रॉम फंडामेंटल्स, देन वी आर लुकिंग एट दिस स्टिफनेस टेंसर, और इस स्टिफनेस टेंसर के ये 2 कंपोनेंट्स फिर हैं जो हमें मटेरियल पैरामीटर्स चाहिए. जस्ट टू पॉइंट आउट, और अभी हम देखेंगे कि दीज 2 आर नॉट इक्वल टू ई एंड न्यू, देयर समथिंग एल्स, ठीक है. सो ये भी मटेरियल कॉन्स्टेंट्स हैं, लेकिन ये स्टिफनेस टेंसर के कंपोनेंट्स वाले हैं, ये यंग्स मॉड्यूलस और पॉइसॉन्स रेशियो नहीं हैं. Okay, you remember at the start of the lecture I said that there are actually loads of different elastic constants. हम बस choose करते हैं कि particular application के लिए कौन सा वाला suitable है to use. Okay, now with that, let me ask you guys, I'm sure you must have heard of different type of crystal structures, right? So वही जो ये face centered FCC, BCC, HCP और क्या होते हैं, मोनोक्लिनिक भी itself भी नाम होता है, and what not. So वो जो these same crystal structures, they do fall into some of these categories. So let me just ask you to think about, what do you think these face-centered cubic and body-centered cubic crystals fall into out of these? Do you think that they are completely isotropic? Yeah, they're perhaps a little less, they have a little bit more anisotropy. Anybody with any ideas? Please unmute yourself and let us know. Is anyone there?
I'm just thinking they have 90-degree angles approximately, as far as I can remember, but I can't tell whether symmetry in planes में है या नहीं है.
No comment. Okay, so Adnan, that is already pretty good. So you are right about this fact that FCC, BCC, as their names imply, they are face-centered cubic, body-centered cubic. So उनके अंदर क्या होता है कि first of all, these angles are 90 degrees, तो वो orthotropic के अंदर आते हैं. But they're actually even more particular than orthotropic. जिस तरह मैंने transversely isotropic की बात की थी ना, ये भी इसके बाद है, right? उसी तरह face-centered cubic और body-centered cubic जो हैं, वो within orthotropic, these two actually, as the name implies, they're cubic. मतलब ये है कि उनकी जो ये लैटिस लेंथ्स होती है ना, देयर ऑल actually equal to each other. So even within the orthotropic one, they are something known as cubic materials, और I have not discussed them here just क्योंकि कितने ज़्यादा होते चले जा रहे थे. और cubic materials में 3 elastic constants होते हैं या 3 material parameters होते हैं. So I just want to point out to you that even these the standard FCC BCC materials that we're so used to dealing with, they are not completely isotropic. They are actually they are cubic materials and they have 3 material parameters. Just for your extra side information, right? But again, it was just getting too many types of materials in here for us to consider them. Perfect. So just whenever you end up, let's say, considering a particular problem in which you're analyzing a material, do think about can we classify it into a further category of a linear elastic material, then that will help us significantly to reduce that how many properties do we need to define that material. And why that's important is because, so for example, if you're, let's say, simulating it, then it's these material parameters that need to be provided to our software. Let's say it's some finite element software that you're using. तो हमें वो उसको बताने होते हैं कि अच्छा जी अगर वो ऑर्थोट्रॉपिक मटेरियल है तो उसके 9 पैरामीटर्स हमें देने हैं, और अगर वो completely linear elastic material है then we have to provide its 21 components. Perfect. So some simplification, and the simplest, clearly the simplest possible material that we have eventually got to is this one. And I forgot to say कि इससे ज़्यादा और कम नहीं होता. So whatever we do, this is this linear elastic isotropic solid is this isotropic solid is the simplest possible solid that exists. Okay, so whatever we do, we are always for this, even the simplest solid, we do need 2 material parameters to completely define the material and characterize its behavior. Perfect. Acha ji, one more side thing to notice about these materials is that just by looking at the components of the stiffness matrix, we can actually figure some things out. So for example, I want to talk to you guys in particular about what happens when we load some of these crystals up under uniaxial loading. Now, मैंने already discuss की थी कि जब हम sorry, जब हम one-dimensional case को कर रहे होते, so what we actually end up seeing is that we see the lengthening or the extension in the direction of the applied load, and we see a contraction in the lateral direction, right? That is the Poisson's effect. कि ये contraction हो रही है. Now, I want to go back to looking at the stiffness matrix to see कि ये क्यों हो रहा है और कहाँ से आ रहा है. Now remember, for example, isotropic material को देख लेते हैं. इसके अंदर we've seen कि if I'm trying to find my stresses or I'm trying to find them in my Kevin-Voigt notation, then what am I going to have here? I'm going to have my epsilon 1, epsilon 2, epsilon 3, and then my shear terms, right? जो gamma है, gamma 4, 5, gamma 6 कर देती हूँ, just to clarify कि ये वाली shear की terms हैं. So if I apply a stress in one direction, let's say epsilon 1 की direction में हो, then I'm seeing that there's actually also going to be a stress in the other 2 direction because of this strain. That is, in other words, it is this Poisson's effect being caused, the contraction here. But at least these terms are 0. मतलब ये कि कोई shear stresses नहीं arise कर रहे from this. I think it may be better if I show you guys the other one जिसमें these terms are actually non-zero to help you identify what I'm trying to say here.
Can you concept please repeat for me?
हाँ मैं वही करने लगी हूँ अभी इतना clear नहीं था, sorry for that. Just look here, look at the behavior of an isotropic and an orthotropic material just for reference, and I want you guys to keep this in mind. This is an isotropic material. If here I have my strains epsilon 1, epsilon 2, epsilon 3 normal strains, and then the gammas shear strains. मतलब ये, this is going to be equal to the stresses. मतलब ये कि if I let's say have a shear being applied, then I see कि ये सारी terms zero हैं, right? मतलब ये कि जो रो की पहली सिग्मा की पहली terms होंगी sigma 1, sigma 2, sigma 3, and then the shear one sigma 4, sigma 5, sigma 6. If I have just a shear strain, just these terms, then I will not get any of these normal stresses, because these terms which couple them together are zero. आप multiply करके खुद देख लें, ये पूरा की पूरी row multiply होनी है इस column से, so it's always these values that get multiplied by the shear strains, right? तो अगर मैं कोई shear strain apply करूँ और ये सारी terms zero हैं, तो what I'm getting is कि इन shear strains की वजह से मेरे पास कोई normal stress नहीं होगा, only इधर terms हैं, मतलब ये कि only मेरे पास shear stresses cause होंगे. Right? That makes sense. Correspondingly, the other thing that happens as well. That is, if I just have normal strains acting on it, then normal strains के कौन से columns हैं? It's these 1, 2, 3 column. Then I look here, ये वाली सारी term zero हैं. तो मतलब ये है कि जब मेरे पास normal strain है और जब multiply होंगे वो इन zeros से, तो normal strain से कोई shear stress नहीं cause होएगा in an isotropic material. I hope कि थोड़ा सा बेहतर हुआ है. अभी इसी को देखते देखते ज़रा पीछे जाएं. तो let's go back. Okay, orthotropic और transversely isotropic, तो orthotropic ही होता है एक particular. इसमें भी वही केस है. इसमें भी ये वाली जो terms हैं, ये तीन इधर 3 by 3 here and this 3 by 3, and of course because it's symmetric it will always, they will be the same, मतलब पता चल जाएगा आपको एक से दूसरे का. वो फिर zero हैं, which means के अब listen carefully, which means के shear strain से normal stresses cause नहीं होते और normal strain से shear stresses cause नहीं होते for an orthotropic material. Now let's go back.
Last two lines please repeat.
Last two lines. Okay, let me write it out. Okay, let me go here. Do this, okay? Sigma 1 1, sigma 2 2, sigma 3 3, ताकि ये भी याद रहे कि ये normal stresses हैं. Then we have sigma 1 2, and I'm not quite sure कि अगला कौन सा है, लेकिन I'm just gonna assume कि it's this one, although I may be wrong इन दोनों के order में. Ignore that if I am, because that does not affect what I'm trying to discuss right now. Now we have our stiffness tensor, and then I have my strains. Epsilon 1 1, epsilon 2 2, epsilon 3 3, epsilon 1 2, epsilon 2 3, and then finally epsilon 1 3. Now, what I want you guys to notice is that for orthotropic, and then further transversely isotropic जो हैं वो orthotropic ही होते हैं, but further narrowed version, and then isotropic materials, what do we see is that if I break my 6 by 6 matrix up into 3 by 3 के ये एक, ये दो, और फिर symmetric है वैसे वो, I don't need to define this, लेकिन I'm still gonna do it. This is the diagonal, just to clarify. then if I look at my orthotropic and isotropic ones, I have noticed just now that all of these terms are zeros. Everybody agreed on this so far. Come on, somebody has to answer that. क्या हो गया? Nobody is agreeing on this either?
Yes, ma'am.
Thank you, Rabia. Perfect. So, and then it's symmetric. So these ones are also zero. Now look what this means. This means, okay, let's say if I just have shear strains, तो इन shear strains ने हमेशा इन column से multiply होना है because of matrix multiplication. So if I have shear strains और ये सब ये वाला पूरा portion zero है, तो मेरे पास normal stresses क्या आएंगे from these shear strains? Zero, क्योंकि वो zero हो जाएंगे सब. Conversely, if I just have normal stresses, normal strains, and if I'm trying to see कि उनसे कोई shear stress cause हो रहा है या नहीं, then I look at this portion of the stiffness matrix and I realize, oh, that's zero. So that what means is okay, normal strains only cause normal stresses, whereas shear strains only cause shear strains. For these two materials, because of the fact that the stiffness tensor is zero in these two 3x3 parts of it. Whereas, does that make more sense now? इसलिए मैंने I just wrote it down ताकि you can get a sense of it. Now let's go and see वो जो उससे पहले हमने दो material types consider किए हैं, which is our lovely monoclinic and triclinic materials, and look at them. Monoclinic और triclinic materials के अंदर क्या हो रहा है? That same 3x3 जिसको मैं देखने की कोशिश कर रही हूँ, which is dictating what the shear normal coupling is, basically. We are seeing that there are actually, these are non-zero. इधर ये वाला column है अभी भी. That means कि in this case, even shear strains can cause normal stresses, and vice versa. Even normal strains can cause shear stresses. Now this is something which is quite absurd, but it's true. We have just become so used to looking at an isotropic material all our lives, और इन वालों को हम कभी देखते नहीं हैं, at least अपने early on in our education. That we just हमें लगता है कि वही law होगा शायद, but that's not the case. So just looking at this part, we can see whether there is any shear to normal coupling, or that's what I want to show you now. Is कि if I take those, again मैंने एक normal stress apply किया है या normal strain apply किया, whichever one you want to call it. So isotropic और orthotropic में हमें सिर्फ एक नॉर्मल स्ट्रेन अप्लाई करेंगे, आपको नॉर्मल स्ट्रेसेस मिलेंगे. बेशक श्योर वो दूसरी डायरेक्शन में भी हैं, लेकिन सिर्फ नॉर्मल ही हैं. Whereas if I draw it out for an anisotropic material, that is वो triclinic and monoclinic जो थे, what do we see? Actually, when we apply a normal strain या normal stress, then we get actually some shearing as well, as shown right here. Please note, ये sigma 22 uniform है. I am not, क्योंकि I am sure loads of you are coming from fluid mechanics and you just get too used to there being a profile. This is not सिग्मा 2 इस तरह नहीं इंक्रीज नहीं कर रहा कि जिसकी वजह से वो इस तरह टर्निंग कॉज कर रहा हो. नो, sigma 2 is completely uniform. This is happening because of the nature of the material. That is, there is actually coupling between normal and shear loading by virtue of what their stiffness matrix is. Okay, now does that make sense?
मैम इसकी कोई फिजिकल रियल लाइफ एग्जांपल है?
Okay, so the same as I'd been talking about FCC and BCC materials, as I said, there are actually loads of other crystal types as well. One, for example, being HCP. HCP are still orthotropic. I'm forgetting the name, but there are crystal structures even just within crystalline materials. अभी तो मैं non-crystalline materials की तरफ I haven't even gone there, right? So for example, when I say non-crystalline materials, I mean some polymers. They for sure, because of their molecular structure, can behave extremely anisotropically, such that they will give you this response. लेकिन वही बात कि we have to look at those particular examples for those. For the world of polymers, particularly hydrocarbons and whatnot, I think you guys are all aware कि वो तो बहुत there's just far too much variety in there. So it's just I'm easily falling in कि वो anisotropic है, easy peasy, आगे चले ताकि, if that makes sense. Whereas the crystalline structures, they have fewer categories which are easier to identify and carry forward. Okay, just as one example, if you have any polymeric material which has long chains in it, even biological materials such as skin and whatnot, so उनके अंदर ये लॉन्ग चेन्स की वजह से एनाइसोट्रोपी कभी कभी आ रही होती है, और उसमें यही होता है, आप इसको पुल करेंगे यूं करके, लेकिन ये साहब आपको साथ साथ shear देना शुरू कर देगा, right? And that's because even for the crystalline structure, it's because these molecules, the structure of this thing is able to couple कि वो normal की वजह से it starts to slide or shear or rotate. Okay. So again, depends on what you guys end up doing. Many people end up going into biological materials in particular, and they have such a vast variety of the constitutive relationships that it's not that complicated. It's just that you do need to be a good mechanical engineer to understand what's happening. Whereas often in अगर कोई लोग biology से आ रहे हो, they tend to miss these intricacies, और फिर इसी किस्म की interdisciplinary fields में आपको let's say कोई mechanical behavior of biological materials पे काम कर रहा हो, just as one example, वो उठा के उसको isotropic assume करके अगर करे चले जाएंगे, so how meaningful are those results? So that's just what I'm trying to say, कि be careful about these things. Research में, you are the one who is policing yourself, so you have to be the one to be careful कि are your assumptions actually correct or not. Okay, right, so I hope that clarifies. Any other questions regarding all these material symmetries and whatnot? So we have managed to come down from our 81 to 2 material parameters for an isotropic material. Right, so now let's just, if there aren't any questions, I'm just gonna take a bit longer, a few more minutes, to look at this simplest type of material. I know कि हम लोग कितने सालों से इसी को देख रहे थे, लेकिन थोड़ा सा और आगे इसी को देखने दें, just to elaborate on कि वो stiffness matrix की components को हमने कैसे find करना है. So for the, I'm going to use the isotropic solid as an example of how to do that basically. Okay. Okay, so As I've already said, there are two independent material constants. We can choose them to be any two of the elastic constants. So for example, in the slides I had noted down as C11 and C12, whereas as I said you could also use the Young's modulus and the Poisson's ratio. और अगर हमें कोई भी और material constant find करना हो, for the isotropic material, then any third one is related to these two, or whichever combination of two you want to use. So for example, the shear modulus for an isotropic material is given like so, right here, right? Because only दो independent है, बाकी कोई भी तीसरा या चौथा या पांचवा जो है आप उन दो की terms में define कर सकते हैं. Even to the extent that we get these nice little tables, Wikipedia it, or even I think in our textbooks of Lie, you get these tables which list how one elastic constant is related to any combination of two other ones. So for example here, we shear modulus and bulk modulus that I'd introduced to you right in the beginning of the lecture, this is how they're related to Young's modulus and the Poisson's ratio. ठीक. So point is कि हमें सिर्फ दो find करने हैं किसी तरह. Now let's see how we tend to do that. So first of all, what I want to point out is कि we assume our material is linear. ये तो बात अब सबको याद है. Linear elastic था, right? Linear elastic और उसके बाद isotropic. अब हम बड़ी precise तीन चीज़ों को use कर रहे हैं. Now the point of the linear is very important right here. Okay, so if I've assumed that my material is linear, then इस केस में भी linear का वही मतलब है जो maths के केस में linear का मतलब होता है. That is that if I have a linear function, just to explain this a little bit more in detail, if I have a linear function, let's say f, then the function की जो भी output है, if I have the sum of two inputs, fa plus b, is actually equal to just the input a से जो output है उसका, plus on top of it जो भी b से output है. That is, the output due to the sum of inputs is actually equal to the sum of the outputs from the individual inputs. Oh my god. Whew, mouthful. But I think written out you guys get the picture, right? That's what linearity implies. Not just कि वो ये है, उससे एक और चीज़ consequence भी आ रहा है, which is the one that I've labeled right here. That is that this principle of superposition holds true for linear materials. Superposition meaning that we can superpose its outputs, its response for separate inputs. Okay? So हम यही use करके इस isotropic material का linear isotropic material का को characterize करेंगे. What we're going to do is I'm going to take this initial material and I'm actually going to perform three tensile tests on it, three uniaxial tensile tests on it. So first test that I'm going to do is this uniaxial test about the x direction. Then the second one is going to be the uniaxial test about the y direction. And then the third one is going to be a uniaxial tensile test about the z direction. Now comes the interesting part. Now I can analyze each of these tests separately. So for example, if I apply this tensile loading in the x direction, I know the strains that I'm gonna get. I know that in the axial direction, that is in the strain in the axial direction is just going to be stress divided by the Young's modulus. Why? Because I know that 1D के अंदर isotropic material का uniaxial stress is just equal to Young's modulus times the strain. But I actually also know that y और z direction में क्या stresses होंगे. They are related by the Poisson's ratio. So when I apply this sigma xx, I actually know कि क्या strains set up हो रहे हैं in each of the x, y and z directions. प्लीज़ नोट कि वी रिमेंबर कि दिस वाज एन आइसोट्रोपिक मटेरियल जिसके अंदर कोई नॉर्मल शेयर कपलिंग नहीं थी, इसलिए जब मैंने नॉर्मल स्ट्रेस अप्लाई किया है, सो आई एम ओनली गेटिंग बैक नॉर्मल स्ट्रेन्स, नो शेयर स्ट्रेन्स. Similarly, if I apply the YY stress, तो फिर उसका version of axial strain and उसके Poisson strains आ जाएंगे. And similarly for the Z direction. ठीक. Now if you remember, हम general 3D motion को figure out करना चाह रहे हैं. मतलब ये कि हम वो पूरा जो हमारा सिग्मा आई जे जो 6 कंपोनेंट्स 6 इंडिपेंडेंट कंपोनेंट्स है उन तक पहुंचना चाह रहे हैं, which means कि we're gonna have these normal, all of these normal stresses applied at the same time in addition to the shear stresses as well. So I'm going to bring the shear stresses in a little bit later, but let me first just tackle what happens if I have all 3 of these normal stresses applied at the same time. Then if that's the case, then I just can superpose my strains for each of my 1, 2, 3 tests, right? और इसलिए मेरा epsilon xx, the normal strain in the xx direction is just going to be a sum of the strain caused by the xx stress, the yy stress, and the zz stress. And similarly for epsilon yy and epsilon zz. Finally, shear stresses रह गए हैं. मैंने आपको कहा मैं पूरी general, I'm going all out, right? I want all of my stresses applied on the body. So now we know कि shear stresses अगर act करेंगे तो उनकी, if I go back and look at my stiffness tensor, पीछे जाना पड़ेगा ज़रा सा, but if you guys just recall, then in that case there is no Poisson's effect, and all that we get is कि जिस direction में भी shear stress apply किया है उसी direction का shear strain हमें मिल जाता है. Okay, I think it's worth going back. Let me show you guys. Sorry for this. Yes, right here. Right here. You see that only the diagonal terms exist in the shear ka case mein. These terms are 0. Or it was these terms जो Poisson's effect cause कर, मतलब को represent कर रही हैं basically. Whereas जो ये the diagonal terms है वो directly उनकी relationship show कर रही हैं. Yeah, I know that maybe this all might seem too complicated, but you guys have to stare at this for a little while and think about the multiplication that's happening to figure these small intricacies out. और वही मैं आपको कह रही हूँ, ये बैठी हैं हमारी Poisson's वाली terms for the normal directions, या for the normal strains and stresses. Whereas in the shear case, these are 0. That is, there is no Poisson's effect in the case of shearing. I wonder if you guys had ever thought about that. Okay, why is the Poisson's effect just in this? Just for the normal strains, right? So here I was just jotting down nice and easy my shear strains being caused by my shear stresses. Now finally I've got all of my stresses acting on the body, on the specimen, so I can just put them all together in my, वही सारा जो पीछे अभी लिखा है, in my matrix form, combine it all up. ये जो पीछे अभी मैंने सारी 6 linear equations लिखी थी, these 3 and these 3, so just combining them together in matrix form, I get this thing right here. And now let's link this back up to our continuum analysis that we had done, which is to note that we'd already seen that the matrix that relates strains to stresses is our compliance matrix. And if I invert this, if I invert it, then I get compliance wali ko invert karen, so I'll get my stiffness matrix. So that's what I've done right here. Sorry, that's what I've done right here. And I've just inverted my जो ये equation इधर थी to get my stresses in terms of strains. Now this thing right here is our familiar stiffness matrix, but the only difference being कि याद करें कि जब मैंने आइसोट्रोपिक सॉलिड के लिए C वाले मटेरियल कॉन्स्टेंट्स में लिखा था, देन आई जस्ट हैड C11, 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 C12, C12 और फिर सिमेट्रिक तो है होना ही है उसने. एंड देन देयर वाज समथिंग राइट हियर एज वेल जो मुझे थोड़ा सा भूल रहा है. इट वाज C11 माइनस C12 डिवाइडेड बाय 2. आई एम फॉरगेटिंग, सो आई अपोलोजाइज. इट्स सम वैल्यू, ओके. और ये सब जीरोज थे यहाँ पे, ये भी ज़ीरो ज़ीरो थे, एंड सो ऑन. Compare this to this one, और फिर we've figured out कि what are our stiffness tensor component C11 or C12 in terms of the Young's modulus and the Poisson's ratio. ठीक. So we don't really need to be doing that, लेकिन I am still gonna manipulate this even further, or क्योंकि there's a convention that is used. So people tend to stick to corresponding elastic constants, right? What I mean by corresponding is that Young's modulus or Poisson's ratio, they go together. So people tend to use this. या फिर G, shear modulus आ जाता है. मतलब लेकिन यही सबको साथ use करेंगे to define the material. या फिर if someone is working in a very heavily continuum mechanics based concept, then they tend to use these guys. So they will use C11 and C12. But then in continuum there's also another one जो अभी I'm going to introduce. There are two more elastic constants which are commonly defined. Oh, I was right about this. This was C11 minus C12. Sorry, so ये रही वही stiffness matrix. Now these, as I said, there are two new elastic constants that I want to introduce again because it is a convention and you'll see why people have come up with those, which are these lambda and mu, known as Lame's constants. Okay, or lambda or mu are just these things defined right here. Okay, lambda is a function, is just defined in terms of E and nu, like so. और म्यू जो है वो shear modulus ही है basically. That's a good thing, ताकि ये at least तो नहीं याद करना पड़ेगा. So just note कि mu is the shear modulus. Now, then what happens when we define lambda and mu like this is because ये जो हमारी stiffness matrix थी उसको हम बहुत ज़्यादा simplify करके लिख सकते हैं. मतलब ये कि ठीक है ये C11 C12 में भी ठीक था, लेकिन एक और आगे का step देखेंगे क्या होने लगा है. If I use lambda and mu, then I can actually write down my stiffness matrix like so. ये वही stiffness matrix है जो अभी पिछली slide पे given है. Only ये नए जो दो हमने define किए उसकी वजह से हम उसको इन दोनों की terms में मज़ीद simplified तरीके से show कर सकते हैं. ठीक. और मैं आपको ये दिखाना चाहती थी कि इसीलिए ये 2 mu plus lambda जो है that does lead us back to this term E multiplied by 1 minus nu divided by 1 plus nu multiplied by 1 minus 2 nu. वही चीज़ आ जाती है. इसलिए ये diagonal terms, just satisfy yourselves, this is correct, this is the same thing on the last slide. और अब हम एक और दफ़ा वही shear strains को swap करने लगे, which is के अभी तक हम वापस हम engineering shear strains में थे. Let me go back to tensorial shear strains, or the reason being if I go back to tensorial shear strains I can put back the 2 in here such that अब the nice thing is कि सारे diagonal terms पे एक तो 2 mu आ गया, फिर only on the normal stresses वाले पे there's a lambda in there. Now the useful thing about that is that now this matrix equation can actually be written in an extremely compact form in index notation, in our standard tensorial index notation. मतलब ये कि I want to go back, I am panicking कि ये क्या होना शुरू हो गया, ये कॉलम कहाँ से बन गया, मेरा वो मेरे पसंदीदा सिग्मा ij's और एप्सिलॉन ij's कहाँ चले गए हैं. And just looking at this column wali matrices and so on, I can figure out I can write out this equation as in tensor notation to represent it. और देखें what's happening. This is very very clever. So just be careful and take a look at what's happening. We're saying कि जो भी sigma है, let's say sigma xx, tau xy, whatever it might be, या फिर let me also write down the index notation of it. उन सब के अंदर उसका corresponding strain हो, जो भी हो, मतलब सिग्मा xx के अंदर एप्सिलॉन xx होगा, tau xy के अंदर ये एप्सिलॉन xy होगा, और सब के साथ मल्टीप्लाई क्या हो रहा है, 2 mu. So 2 mu multiplied by the strain, but then just add on top of it add on top of it what? Just lambda, but lambda किससे multiply हो रहा है? Only by the trace, only by the diagonal, ये epsilon xx, epsilon yy, epsilon zz के साथ. ये देखें वाकई यही हो रहा है, ये लैम्डा तो सिर्फ इन्हीं से मल्टीप्लाई हो रहा है, not with the shear terms. So that's why lambda with the trace of epsilon multiplied by the identity. Ignore the identity part, वो अभी इतना ही हम समझ लें तो that's enough. The longer we stare at this expression and think about it, the more it is going to make sense to us कि yes, indeed, this matrix notation या matrix equation is represented like so in tensor या फिर in index notation. Okay. Now a few comments right here is के इसकी tensor notation I think is easier to look at and understand, whereas index notation में because this trace is being multiplied by an I, so just go back and revise के the identity tensor is actually the Ronecker delta. So इन दोनों की जो multiplication है उसको क्या लिखना होगा हमें basically. So be a bit careful about this. Now this, oh I've missed out. Now this expression right here in tensor notation is the constitutive stress strain relationship for a linear elastic isotropic मटीरियल. इतनी लंबी सारी कच कर करके हम इधर तक पहुंचेंगे और पहुंचे हैं. इससे पीछे तक एज यू गाइज माइट हैव नोटिस्ड कि वो जो बाकी मटेरियल टाइप्स थी उनको हम मैट्रिक्स फॉर्म में लिखने के अलावा और कुछ नहीं कर सकते थे. ओके, whereas this isotropic material, that one can neatly and compactly be represented back as tensors like so. So we've come back to where we started, which is that our stresses, our strains are tensors, and we started with our stiffness tensor, but then we saw that stiffness tensor can actually be simplified in terms of its number of independent components. When we get to our isotropic solid, we just have two elastic constants. Now, depending on the particular problem, it's up to us to choose which one we want to use. So we can use Young's modulus, shear modulus, or Poisson's ratio, or we could use C11, C12, or we can use these Lame's constant lambda and mu. All that requires is कि फिर हम अपने जो generalized मतलब ये कि 3D वाला Hooke's law है उसको ज़रा उन वाले elastic constants की terms में लिख लें. Now as you can see in C11, C12 it was this one, लेकिन this expression cannot be written down in tensor notation compactly. Whereas Young's modulus or Poisson's ratio में तो वो ये है, and I think you can see that this is not so straightforward. याद रहे हम 3D, we're talking about generalized, so we're talking about the three-dimensional behavior of the material. इसलिए Young's modulus or Poisson's ratio is less useful. 1D में तो sure, go ahead. Young's modulus or Poisson's ratio define ही वो 1D के लिए हुए थे. Whereas we are now talking about 3D constitutive behavior. So that's why these Lame's constants got introduced, because they allow us to compactly write down the constitutive equation in tensor form like so. Okay guys, so there was a lot of information packed in here. I hope it was all new and interesting to see how the simpler things that we've been doing for so long there's a pretty long story behind them. So I'm gonna stop here, and the next time we'll pick up for the isotropic solid and see where we can go further from this constitutive, where we can take this 3D constitutive behavior of the isotropic solid further. Right, so that's it from my end. I'm around for any questions.